to have Deborah Mayo finally visit us. We've been trying to have you visit for at least 3 years now, maybe. But we're glad to finally have you here and to talk about our new book. I believe that's the title of the book, Statistical Inference as Severe Testing, How It Gets You Beyond the Statistics Wars.
Thank you. And of course the title is How to Get Beyond, but here I'm going to try to answer it. Okay, well thank you very much for inviting me. And I certainly do want to participate in this group, which sounds great. And insofar as, I am spending more time in New York, I would hope to come. And now I see how easy it is to get here. Okay, and so now, let me just see if I know how to do this. Okay. Is this good? Okay, so start with the statistics wars. What are they? They're fascinating. They are at once ancient, but also up to the minute. The ancient part is that they really deal with one of the oldest questions, namely, how do humans learn about the world in the face of error? And they are also up to the minute in the sense of being the engine behind today's discussions about high-profile failures of replication and so on. A big question is, what's the role of probability in statistical inference? Does probability mainly enter in order to control the rates of errors in some long-run application? Or does it arise to represent degrees of belief, support, confirmation in claims? The wars between frequentists and Bayesians have been so contentious that everybody wants to believe that we are long since past them. After all, nowadays we have unification and eclecticism. People are free to use methods from any place as long as they work. But the truth is that long-standing battles still simmer below the surface in today's debates about scientific credibility and how to restore it. And merely the fact that we can get an agreement on numbers when in fact different accounts are measuring different things just leads to a kind of statistical schizophrenia, and people aren't clear what we're talking about. So I say that we really need to brush off the dust on the pivotal debates and get back to them in relation to today's statistical crisis in science. And what that crisis really points up is the problem that occurs precisely when we have these high-powered methods that make it easy to find impressive-looking effects, even though they're spurious. So I start with a very simple tool, namely, if nothing has been done to rule out flaws in a claim, then that claim has not passed a severe test, that we don't really have evidence for it, that we haven't probed it. It's a sufficiently general idea, I claim, to apply to any methods now in use. And in this account, the idea is that we use probability to evaluate and control how capable methods are in uncovering flaws in inferences. It doesn't mean, by the way, that we're always doing formal testing. The same account can apply whether we are doing model building or prediction or explanation or estimation. What's more, you needn't accept the basic philosophy to use it to peel away some of the layers behind the statistics wars, or so I say. So I say, let's go on this philosophical excursion in my book, taking the severity principle along with the aim that we want to find things out and don't want to be obstructed in this goal. Let's set sail on this philosophical excursion to understand how we got to where we are. And in so doing, we will look at competing groups. We will look at the shifting alliances and peace treaties and family quarrels and so on. And this picture of this ship is actually in the book, in the preface, which is pretty cool, I think. It's not the ship I gave them, but okay. So, do you want to stop me with, you're free to stop with questions. Hi. Well, let's start with this claim from John Ioannidis in the famous 2005 paper, where he says several methodologists have pointed out that the non-rate of replication is a consequence of the convenient yet ill-founded strategy of claiming conclusive evidence. Okay, conclusive research findings solely on the basis of a single statistically significant result. No wonder most claims are false. Do people do that? I find that really amazing that they would go to a substantive finding on the basis of a single statistically significant result. After all, Ronald Fisher, the originator of significance tests, made it clear that we're not interested in isolated records, but a reliable method of procedure, that you don't have grounds to say you have evidence for a real phenomena unless you know how to conduct an experiment that would rarely fail to find a statistically significant result. So what do we mean by talking about significance tests? And this is from a paper that I wrote with David Cox. We are interested here in, this is clearer, to test the conformity of data with some test or null hypothesis, H0, in some respect. We start with a function t of the data, a test statistic, such that the larger the value of the t, the more inconsistent the data are with H0. And then the p-value corresponding to the observed value of t is the probability of getting at least as large or larger a value of t under the assumption that the null hypothesis is an adequate description of the data generating process. The testing reasoning is very straightforward. If even larger differences than observed occur fairly frequently under the null hypothesis, then there's scarcely evidence of incompatibility with the null hypothesis. Small p-values indicate at least some underlying discrepancy from H0, because very probably you would have seen less impressive differences than you got were H0 correct. Of course, this still isn't evidence of the kind of genuine statistical effect that Ioannidis talks about, let alone is it evidence for a scientific conclusion, which we can distinguish with the Hstar. And this, of course, is a well-known fallacy going from statistical to substantive. It's an example of a fallacy of rejection, because Hstar, the substantive hypothesis, has made claims that haven't been probed by the statistical test. And really, I think the moves from the statistical to the substantive inferences should be getting a lot more attention than they are in replication research. But at the very least, your statistical account should block them. With Neyman-Pearson tests that came around to improve on Fisher, we do have such a block. Here we have a null and an alternative hypothesis that exhausts the space, exhausts the parameter space. Here's one example where it's a one-sided test, no effect versus some effect. Okay. So at least this fallacy of rejection is blocked, because rejecting H0 only indicates the statistical alternatives, how discrepant they are from the null. And of course, this introduces the type 2 error, that is the failure to reject the null when you should.
So why does this block in a way that Fisher didn't?
Sorry?
Why there's no mention of Hstar? Why is, either by Fisher or by Pearson in your exposition, so why is this one blocking it and the other one not?
Actually, they do both talk about it. Fisher was quite clear that to infer some sort of causal claim, you need to have several tests and you need to have them varied in all sorts of ways. So he did make claims about that you're not allowed to go to something like a causal conclusion, okay? But here I'm saying that if you follow the Neyman Pearson, you really wouldn't, at least insofar as you were doing this statistical inference, you would not have gone beyond. I mean, you could still make that mistake. And the other mistake you can make that I'll talk about is inferring a discrepancy larger than's warranted, even though you're staying within the statistical realm. So you're not free of it, but at least you're not wondering what particular inference we can make. It's rather restricted once we've specified the test. That's all I mean.
So the
okay.
Your point is that by talking about H1, you sort of made clear that you're not talking about Hstar. Is that the point?
Yes, I believe so.
Yeah.
And so I maybe just a way to get to present that point.
But are you justified in, is that to suggest that you're justified in saying something conclusive about H1 if you reject the null hypothesis, you're also accepting the alternative?
Well, this is the thing. If you have the null and the alternative exhaustive, as I would say that you should, then you can infer evidence for the alternative. I don't happen to think that's enough. I think you want to be able to say something about the discrepancy that's warranted, whereas they don't. Okay, but really it was a major problem with Fisher, and it's a problem that's with us today, and that's why you get people like Ioannidis saying that people go directly to whatever their psychological or their theory is. Okay, and that's why I mention it, because at least you're somewhat restricted in that.
Maybe you don't mean this as primarily a historical talk. I'm not sure. I'm not sure how much you mean this to be historical.
Maybe not, but I think it is, because I think Neyman Pearson were extremely worried that he allowed too much leeway, exactly the kind of worry that we have now, too much leeway, even in a post-data way, to decide which discrepancies you should look at. And Fisher historically said, look, the researcher knows what difference he's interested in. We don't need to have this specification. And the fact that he might know doesn't mean it isn't very useful, and exactly what Neyman Pearson were trying to do is see if they could justify choosing some discrepancies rather than others, and that's how you get to the optimality criteria and so on. But I wasn't trying to make too much of a point here on the history, but there is a historical background for it.
The history is very interesting. But I said I don't know how far you want to go into history, because I had a historical question, which is one that I puzzle over, because I teach this.
Yeah.
I have the chance. I'm actually getting to teach history.
That's fun.
I've been trying to teach this. And I may be exaggerating my students when I tell them that Neyman and Pearson were very concerned about fixing that significance level, whereas Fisher was not so clear about it. Is that a fair thing from your reading?
Yeah, there's a long story. I happen to spend a lot of time in the book unraveling that story. How much was it that he was firmer or less firm? Actually, I think that Fisher was pretty routine in setting 0.05, and if you ask somebody like Eric Lehman, Neyman's student, he'll say that was really Fisher's idea. Neyman Pearson always said, balance the two. And we're rather opposed to this idea of this rigid fixing.
Well, maybe my question is a little different. My question was the p-value issue.
Yeah.
Whether you could wait till after you saw the data to talk about what the level was.
I think and
it seemed to me that Neyman and Pearson were very clear. You don't wait after you see the data, and Pearson was not so clear. Is that fair?
Pearson not so clear. This,
Pearson
again,
not so clear, yeah.
is complicated. I'm prepared to say that I think that Fisher and Neyman and Pearson would pre-specify a p-value or a type 1, type 2 error. But really, it's a great story. I don't know how much, I should get into it about, who was a little bit more rigid about that. Well, let's see what happens, because we will go a little further on this. But one thing, okay, so this relates to your point, is I claim that Fisher, Neyman, Pearson is not the incompatible hybrid that many people make out. This is my argument, that they both fall under tools for, this is Birnbaum, appraising and bounding the probabilities of seriously misleading interpretations of data. And we can call these error probabilities. And I place all of these under the rubric of error statistics, which really is clearer than titles like frequent tests. And under this, I'd put confidence intervals and both kinds of tests, resampling, randomization, and other things besides. It's true that people talk about this inconsistent hybrid where Fisher was more inferential than Neyman Pearson, who are said to be mainly interested in long-run performance. But I really think it's a mistake that mathematically they intertwine, and that this incompatibilist view results in p-value users being robbed from features that they need from Neyman-Pearson tests like power, and wrongly supposes that Neyman-Pearson testers have only these fixed error probabilities and are absolutely not allowed to report the attained p-value. And again, I'd refer to Eric Lehman, who's Neyman's student, who makes it clear that it's good practice to determine the smallest significance level associated with the actual observation, the p-value, which gives an idea of how strongly the data contradict the hypothesis and enables others to reach a verdict based on the significance level of their choice. One main thing, though, is that both groups of testers emphasized in one way or another that it's easy to lie with statistics by selective reporting, that sufficient finagling, cherry picking, significance seeking, multiple testing, and various different terms, trying and trying again, may practically guarantee a preferred claim, get support, even if it's unwarranted by evidence. And here we get to this minimal requirement that says a test has little or no capability of finding flaws, then the agreement between the data and the hypothesis is poor or no evidence if it couldn't find some counter to it. So I say that such a test fails this minimal requirement for a stringent or severe test, or Popper would say these agreements are too cheap to be worth having. It's true, Neyman Pearson didn't put it exactly in the severity terms, but our severe tester does. And if you trace out the history, you'll see, many connections with what they actually do say. One thing is looking at tests this way, as severe testing, alters the role of probability. So the probabilism idea, I'm calling it that, is that probability arises to assign a degree of probability or confirmation or support or belief in the data, in the hypothesis given the data. It can be absolute or comparative, Bayesian, likelihood-est. I'm going to put them all under this heading. As opposed to the performance artist who sees probability as ensuring the long-run reliability of methods, coverage probabilities, behavioristic views of Neyman and Pearson, Fisher at times. But think, what happened to using probability to assess the error probing capacity? It seems to me that neither of these directly captures it. Good long-run performance is a necessary but not a sufficient condition for severity. And the interesting thing here is it suggests a revision of the role of error probabilities that goes beyond what significance testers usually say. Ask yourself what bothers you with the selective reporting we hear about, with cherry picking, with stopping when the data look good. It's not really a problem about long runs. When you see this guy, I don't know if you can see him, who's fishing for p-values and so on. We criticize him because he has not done a good job in the case at hand of avoiding known sources of misinterpreting data. It's true that if you keep on this way, it will have poor long-run performance, but we very clearly say that he hasn't done a good job in the case at hand. This is poorly warranted and poorly tested, and this, I think, is the key to see the data dependence and the relevance of error probabilities for the case at hand. So to compare these three views of probability in terms of when a claim is not warranted. For the probabilist, it's not warranted unless the claim is true or probable or gets a probability boost, made comparatively firmer or something like that. For the performance artist, it's not warranted unless it stems from a method with low long-run error. And for the severe tester, it's not warranted unless something, hopefully a fair amount, has been done to probe ways we can be wrong about the claim. Okay. And one of the key functions of severity is to identify problematic selection effects, because not all data-dependent selections are problematic. So I define biasing selection effects this way, as when data or hypothesis are selected or generating or test statistic is specified in such a way that the minimal severity requirement is violated or altered or incapable of being assessed. A standard example, and this is from Morrison and Henkel way back in 1970, if you're testing maybe 20 sets of differences and just one seems large enough to test, and it turns out to be at least nominally significant at the 5% level, the actual level of significance is more like 64%. Of course, that assumes independence, which we don't have, but the point is that there's a difference between what they call the nominal or computed level and what the actual probability of erroneously spewing out a report would be. He reports such results would be difficult to achieve. This is our p-hacker. He reports the results would be difficult to achieve under the assumption of H0, when in fact the results are rather common under H0. There are many more ways to be wrong with the sample space that he actually used. Or formally, he's saying that the probability of the p-value being less than observed under the null is small, when in fact it can be high. We get a kind of replication paradox, I find, in today's replication research. First, what is the crisis of replication? It's the fact that it seems too difficult to replicate the small p-values that other people got, at least when we use more stringent protocols, when we pre-register our hypothesis and so on, which might lead to the complaint that it was too easy to get low p-values the first time. But think about that. That can only be saying that it's too difficult to get the low p-values if you cheat or if you're allowed to finagle or ignore unwelcome effects and so on. And so it suggests simply that the correct way to be using the p-values is either to announce that you engage in the p-hacking or to adjust the p-value in such a way that it is now closer to the actual value. And yet not everybody thinks you should do that. In fact, there are some leaders of today's Meta Research Institute who say we should not adjust the p-value in the case of selective reporting, and in fact it makes no difference. This is Steve Goodman, who's one of the directors of the Meta Research Innovation Center along with John Ioannidis at Stanford, who says that this is a problem for frequentist inference, for wanting to adjust. Adjusting the measure of evidence, says Goodman, because of considerations that have nothing to do with the data defies scientific sense. And as I mentioned, to his credit, he's open about this, that this is a particular philosophy of evidence that he follows. Any questions? And it's one that is associated.
I'm not familiar with that. Could you go back to that slide and
go back to it?
Yeah. So he says, we know multiple comparisons is going on, but when we do meta research, we'll ignore that. Is that what he's saying?
Well, actually, he's one of the directors of this outfit that's called Meta Research, and I'm not saying that he would be doing meta research, whatever that is, when he's discussing this problem, but clearly he's talking about inference, he's talking about the standard idea that you do need to adjust for multiple comparisons and so on, and he's saying, no, according to his philosophy, we don't need to. And it's based on something that I'm going to now mention in the next slide, based on a notion of evidence that says, really, the evidence comes through the likelihood, and so they're not going to be influenced by these error probability considerations. See what I mean? But I guess what they take themselves to be doing, I always tell them that meta science is a philosopher's term, and that they've sort of co-opted it. And so I guess they just mean, being critical of how the research methods being used. And his view, which seems surprising, it's not just him, is that we shouldn't be doing these adjustments. Because on this view of evidence, the import of the data is via the ratio of likelihoods of hypothesis. Now, likelihoods are often misunderstood because the data are fixed and the hypotheses vary, right? And they're not probabilities. If you have a perfectly fitting hypothesis, you will get a likelihood 1, and you can have many, even rival hypotheses that perfectly well fit the data. An example of somebody who based a whole account on this is Ian Hacking, and so this did not use prior probabilities. It was just looking at likelihoods. He calls it the law of likelihood, that data support H0 less well than H1 if H0 are less likely in this technical sense of likely. But he dropped it not too much longer afterwards. And the real reason that he did is, as George Barnard puts it, there always is such a rival hypothesis, H1, namely, things just had to turn out the way they do. So you would be able to get a better fitting alternative with high probability. So here's where the error probability idea enters. This is Newman and Pearson, who say, to fix a limit between a small and a large value of a likelihood ratio, we have to know how often such values appear when we deal with a true hypothesis. So we're going to look at the probability that H0 is less well supported than H1 for some H1 or other, and that might be high. Okay, so that's the second level, you might say, that the error probability person looks at to critique the result. And in fact, all error probabilistic notions violate this likelihood principle, even without selection effects. Okay, so first, here's a quote from Dennis Lindley, a subjective Bayesian, points out sampling distribution, significance level, power. They all depend on something more than just the likelihood function, something irrelevant in Bayesian inference, namely the sample space. And he means post-data, because they would all use them pre-data. And Roger Rosenkranz, who I was talking about with somebody a minute ago, that the likelihood principle implies the irrelevance of predesignation of whether the hypothesis was thought of before or introduced to explain known effects. Here's another kind of example where error probing capacities are altered. It's not just data dredging. It can also be with stopping rules. And this is a famous example where you have a two-sided test in English, no effect versus some effect. And this is really normal distribution testing, I should mention. But instead of fixing the sample size n in advance, okay, you can have it that n is determined by a stopping rule. And the stopping rule tells you to keep sampling until you can reject the null hypothesis at some nominal level, let's say 0.05. Okay. Having failed to rack up enough successes, 1.96, or we can call it 2 standard errors after 10 trials, you go to 20, go to 30, etc., until you can eventually stop and declare statistical significance. You can see, again, the actual significance level is going to be much higher than the 0.05, and we can compute about how much it would be depending on when it stops. This is considered a proper stopping rule, by the way. That means that it is known to stop with finitely many trials. So Edwards, Lindman, and Savage, this is a very crucial paper of theirs from 1963, who say, if an experimenter uses this optional stopping procedure with probability 1, he'll eventually reject any sharp, that is the point null hypothesis, even though it's true. And understandably, they observe, the significance tester frowns on this, or at least requires these adjustments of p-value. Imagine if, this is from the book, so it's in red. Imagine if instead of an account advertised itself as ignoring the stopping rules and said, the irrelevance of stopping rules is a great thing. It restores to statistical inference the simplicity and freedom that had been lost by classical emphasis on significance levels, in the sense of Newman and Pearson. So here I'm telling you who's speaking, so there's no surprise. It's the same authors who had warned us that to ignore stopping rules is to guarantee rejecting the null, even if it's true, say it's irrelevant. Are they contradicting themselves? Well, no. It's just that what looks to be, and indeed is cheating from the significance testing perspective, is not cheating from their particular Bayesian perspective. So cheating depends on statistical philosophy. So it ought to be front and center in some of today's controversies, but it usually isn't. Now, replication researchers, I say, rediscovered that data-dependent hypothesis and stopping are a major source of spurious level. Well-known statistical critics Simmons, Nelson, and Simonson place at the top of their list the need to block flexible stopping. They say authors must decide on the rule for terminating data collection before it begins, and they should make it clear in their article. In fact, they've got this 21-word solution which says that the researchers should put in the methods section the stopping rule and also the particular hypothesis and the way they're going to condense data and any subgroups and any primary endpoints, and all of that should be put in there. And the reason I call this that they're rediscovering it is that they declare themselves surprised at how much these things can affect. They thought it was like jaywalking, but it's more like robbing the bank, okay? Berger and Wolpert, and this is Jim Berger, had written a book called The Likelihood Principle in 1988 that said it seems odd that a frequentist needs to know the stopping rule. Doesn't data, won't they just speak for themselves? Why do we need to know what people intended to keep going? That's like their intentions locked in their head. And it's true that this intuition is satisfied by inference by way of Bayes' theorem, and I point out at the beginning how stopping rules drop out. Very, very quick, very easy proof if you accept the likelihood principle. But you might think that current day contemporary replication researchers would never follow this Edwards, Lindley, and Savage kind of an idea when it came to optional stopping, given they've got the 21-word solution, at least some of them do. But in fact, many of them do echo Edwards, Lindley, and Savage. And this is Eric Wagenmacher, who's in psychology, who echoes them exactly, saying, if the sampling plan is ignored, you can always reject the hypothesis even though it's true. Some people think that's reason to worry about the stopping plan or the sampling plan, and they say, but in fact it's a mistake, and we can prove this mathematically that it's a mistake to care, but the proof assumes the likelihood principle by which the error probabilities drop out. So that position is still around, but is not made very explicit in some of today's debates. And the funny thing is, it's considered a kind of counterexample to the other side for both sides, and this is Rod Little, who says, the optional stopping example is cited as a counterexample by both Bayesians and frequentists. If we statisticians can't agree which theory this example is counter to, what is a clinician to make in the debate?
You lost me with that.
Huh?
I didn't understand. Why is it, how are both sides, you've given examples of both sides?
Yes.
Which side is Wagenmacher?
Okay, he is on the side of the Bayesian, who would say that the stopping rule doesn't matter, even though we can show that you will eventually stop. You will stop with probability 1 and erroneously reject. They say that that's still irrelevant.
Bayesian using it as a counterexample.
Yes, that's correct. And the frequentists will also use it as a counterexample to say, look at those Bayesians, they will allow you to ignore the stopping rule. Okay, and the funny thing is they really do both use it as championing their account. That's the main reason that it's of interest. Okay, well, I mean, there's more to this example, but that's the basic idea. Yeah.
Both are right, right? Huh? It just seems to me both are right, because the frequentist is that if you use classical one without considering the additional sampling mechanism of randomness, so of course you will eventually reject. But if you're considering all this every time you redo the analysis, instead of conditional how do you do the sample, getting everything into consideration, I think the stopping rule, whatever you kind of sequential rejection rule is fine. It's just you need to change in those levels. You cannot fix certain kind of levels.
That you would alter your level.
Right.
But that means you can't ignore it. That means you're taking it into account.
You need into account, right.
Whereas the other side is saying you don't have to take it into account. In fact, it makes no sense to take it into account. And you know, Housen and Urbach, the philosophers who have their well-known subjective probability textbook, will say anybody who does take it into account is showing themselves to be using an account that's irrelevant for science, because scientists would not take intention into account. And so this is a classic war, okay? And I'm not saying there aren't ways they'll try, and I talk about them, but just looking at them is very informative as to what some of the classic wars have been and still are. Yes?
I mean, Bayesians, wouldn't Bayesians incorporate the way the data is observed in their prior?
Well, see, now here, this is a complicated thing. They definitely will appeal to the priors if they want to block the inference, because it's really the only place they can do it. But I don't think they would want to do it by saying it's the stopping rule, because that in itself makes you Bayesian incoherent. Now, I like to say that I'm talking about the classical Bayesian, because a lot of Bayesians now who violate this in various ways. So we can put the term, the classical Bayesian would say you would be incoherent if you selected your prior based on the model altogether. Okay, although the default Bayesians will allow it, but the whole idea is the prior is supposed to represent your beliefs in the hypothesis independently of the experiment that's going to be done to test it. But as I say here, they can still block intuitively unwarranted inferences, okay, even without going against the coherence, and even without error probabilities, somehow with their beliefs. And Richard Royal will say, look, if you're bothered by this, it just means that you're worried about what to believe, and we really need to distinguish evidence from belief. And we really need to have likelihoods plus priors to do that. Okay, and you all know, trying to make inference by Bayes' rule would look like you need to have an exhaustive set of hypotheses. Most of the time now, the Bayesians use comparative claims like the odds ratio or the Bayes factor or something to try to mitigate the idea that you need this catch-all hypothesis, the probability of the data under all other hypotheses. So yes, you can appeal to priors, but there are problems with doing so. Okay, it can work in some cases, but it seems to me it still wouldn't show what the researchers had done wrong. We're talking about researchers who had committed either trying and trying again, or p-hacking, or some other biasing selection effect. So it becomes a battle of beliefs. And really, a lot of researchers believe their data-judged hypothesis. And in fact, it's the believability of things like post-data subgroups that make them so seductive, because once you found them, that you feel that that's really the right thing. If nothing else, it's clearly an additional source of flexibility. And the whole point of this hand-wringing is having too much researcher flexibility in interpreting and generating the data. Okay. And what about the key problem? It seems to be no help in solving the severe tester's key problem, and that would be to distinguish the warrant for a single hypothesis, but with two different methods. Let's say one having biasing, committing biasing selection effects, and another, like a lot of the replication attempts, with pre-registered results with various precautions. Because there's just one and only one hypothesis, you would think they would be the same prior, so somehow the difference is going to have to be reflecting those data generating methods, and that's exactly what's being denied. Now, most Bayesians these days, at least in the last decade, use what they call non-subjective priors, or default priors, or conventional priors. In fact, this is a big part of that unification that makes them think that the wars, aren't with us anymore. So why do they turn to them? Well, for one thing, eliciting the subjective prior seems too difficult, and scientists don't like to do it, and they're not very good at it. And Jim Berger points out that virtually never would different experts give prior distributions that were even close to each other. So these default priors are supposed to prevent beliefs from influencing the posteriors. They are said to be data dominant in some sense, okay? But there are many different ways to do it, to come up with them, and there's been no agreement on the best way. It's also not clear how to interpret them. And one of the things Cox and I say, that if the priors are not considered expressions of uncertainty, ignorance, or belief, then what are the posteriors? And the reasons that they're not considered expressions of uncertainties, they may not even be probabilities, they are usually improper. So there's question about what system to use and how to interpret them. And there's another thing that is a problem with these appeal to the priors to deal with biasing selection effect, and that is some of the criticisms of p-hactors tend to lose their force. I'll explain what I mean. Wanting to promote an account that doesn't turn on error probabilities, the researcher who really deserves some criticism for their biasing selection effects can be given a life raft. Take the example of Daryl BEM. I guess you've heard of this, because some people think that the replication crisis really began with him, okay, where he claimed to show that subjects do better than chance at predicting a certain picture that they're going to be shown in the future. But he admits that he went on a fishing expedition and finally found post-data that it was a certain kind of erotic picture that they could guess better, but more than that, it had to be a certain subgroup of people who had certain superiority complexes or something like that. But the interesting thing is that the Bayesian critics, and Wagemacher is one of them, resort to the default Bayesian prior to a point null that says zero effect. And so BEM can respond to them by saying, well, look, I know you can always discount my statistically significant result that way. And this is BEM's response. Whenever the null hypothesis is sharply defined and the prior on the alternative is diffuse over a wide range of values, then you can boost the probability that any observed data will be higher under the null. Jeffreys-Lindley paradox, Lindley-Jeffrey, it's also called the Bayes-Fisher disagreement, and it really isn't a paradox, it's just showing the difference between a Bayesian and a frequentist analysis. And he's saying you can always contradict my account this way by giving this great big lump of prior probability on zero. So just to see what it is, it's this two-sided test again, and you give the lump on the zero, you start out with it, and you can, in the extreme case, especially as n gets large, wind up with a posterior probability on the null hypothesis that's so high, it's even 1 minus this small alpha. So if you set a 0.05 alpha, it could be 0.95. So clearly, it seems we're coming up with very different conclusions. But BEM is saying, since you can always do that, I sort of discount your result. And this is an important thing if you think about the fact that not everybody supposes that researchers should be subjected to replication research. Some are very angry about it and call these replicationists methodological terrorists who are ripping up science that's built by others. And if you have to appeal to your disbelief to show that my result fails to replicate, I'm even more likely to see you as, bullying, right? And this disagreement is also very relevant to other debates that come up in statistics wars today. Okay, for example, the one that we see that significance tests exaggerate the evidence. So the bottom line is, again, that the posterior probability can be large while the p-value is small. It's a well-known result, and it too goes back to Edwards, Lindley, and Savage. Okay. So to the Bayesian, the p-value is exaggerating, but to the significance tester, the Bayesian is biasing. results in favor of the null hypothesis. And this is George Casella and Roger Berger, who say, by concentrating the mass on the point null, you're biasing the prior in favor of the null as much as possible. And there's this back and forth debate between them and the other Berger, Jim Berger and Selke, in the 1987. But it's also behind the very recent redefined statistical significance wars, as many of you are familiar with, because they too play the game by giving a lump of prior to the null hypothesis, which you might think completely conflicts with the idea that some people say that all nil nulls are false, whereas they're giving a lump of prior to it. Moreover, they don't have to do it that way. They can also get the p-values to be equal to the posterior probability by having a more diffuse prior instead of the spiked prior. So it can range, the posterior can range all the way from matching the p-value to being 1 minus the p-value, leading Stephen Sen to say the reason Bayesians can regard p-values as overstating the evidence against the null is simply a reflection of the fact that Bayesians can disagree sharply with each other as to which prior to start out with. Many of the debates revolve around just the same point. So that's the end of the main talk. I wanted to say, though, that the severe tester certainly wouldn't endorse a lot of today's uses of significance tests. And as far as my own work goes, for at least 25 years, I have suggested ways to reformulate tests, but it just so happens that today's controversies really underwrite this reformulation, in even stronger terms. So I was going to say something now about that, about the reformulation. And yeah, okay.
Well, before you get to that, maybe
Yeah.
I have a question about the last thing you said. I guess
Sure.
The sound quote, but also the redefined thing. If I understand correctly, you're saying that a diffuse prior would correspond to the p-value.
It can be, yes, it can be made to.
And if I put a more spiked prior on the null, then it makes it, I'm biasing it towards the null, right? But in line with your, the title of your talk or the title of your book, I mean, wouldn't putting that spiked prior be a severe test? I mean, isn't that a more severe test?
Well, no, because you see, if you do that, then you might, with high probability, fail to find evidence against, even though there is evidence. Remember, we care about the type 2 error. And in fact, that would be the significance tester's complaint, that here I've got a highly statistically significant result, and you're claiming, because of your spiked prior, not only don't I have evidence of some discrepancy, you're actually saying you have evidence for the zero. So the severe tester would complain on those grounds. Okay. They were finding evidence for the null, even though it had not passed a severe test.
Sure, yeah, but that's if you interpret that as evidence, right? But why? Well, I mean, I don't need to necessarily interpret that probability in favor of the null as evidence in favor of the null.
Well,
It comes from my prior, which I don't take.
Well, what is it when you get a high posterior to the null? If it's not that, if there's not some kind of evidence for the null.
Well, if the prior is subjective.
Yeah, but now the posterior.
Regarded as evidence.
And don't forget, they're saying that the significance testers are exaggerating the evidence. So they're talking about the evidence and the correct way to interpret it. And they're saying the significance tester is incorrectly interpreting it because they're finding evidence against, when in fact, if you do it our way, we not only don't find evidence against, but find evidence for. So they are clearly putting themselves in this comparison of an evidential appraisal, right?
Okay, well then I would agree. I would
Yeah.
agree there's something wrong with that. But I would, but I guess I could see a third interpretation for that, where you don't necessarily take it to be evidence for Where I mean, I see a hypothesis test as a one-way street. You can reject the null hypothesis. Type 2 error is, I don't know. I'm not inclined to accept the alternative when I reject the null. Rejecting the null is
Maybe not.
No.
Well, it depends what you mean by it. You may want to say there's just some indication for it and I don't want to accept it yet or something like that. But in trying to pit the approaches together, and don't forget, they're raising the criticism that they presume is relevant to the significance tester who's not doing posteriors and who could say, I'm not doing that. But instead of saying that, I claim what we should do is analyze how severely the claim that they're purporting, okay, to infer would pass, that this is a kind of way to stand beyond the dispute and see why they are talking past each other. And they could be talking past even more so in giving a different interpretation. But again, they don't see it that way. They think it's relevant enough to change the practice of p-values, as you know. Yeah. Yes?
So, you know, we were talking about Harold Jeffreys, and my mind goes back to what he was, how he put this expression.
Who I'm sorry, Jeffreys?
Harold Jeffreys.
Yes.
This framing, the null hypothesis H naught, I mean, say in Jeffreys' scientific work, it might have really been the alternative hypothesis that he was interested in testing. Is that unfair or wrong? So if you're thinking about severe testing, he might have thought what you're trying to test is a theory that says that something has an effect.
That's something that has an effect.
Yeah. That might be the
null, or the thing you care.
That might be the scientific hypothesis you want to test.
Yeah.
So I know. So here in this discourse that you didn't invent this discourse, but in this discourse that you've put us in the middle of, we take this no effect as the thing we're testing.
But it needn't be. It can be no discrepancy, let's say, from Einstein's deflection effect, which would be your way of stating, a way that Jeffreys could state that we give weight to the Einstein deflection, or to the Newton one, which is, in fact, what he did. You know, he was around in those 1919 debates. It could be. So it could be zero discrepancy, you can see it as. But it's still a point in the Jeffreys, or at least a small range around the point. Okay, so it really wouldn't matter if it was
Couldn't the model we want to test really be that some variable has an effect without saying what the effect is?
It could be, but the way they do it, and really Jeffreys invented this test in order to give weight to a scientific theory that he thought had a prior plausibility. He didn't say to use it for all of these other cases that these contemporary people are using it for at all. He had to do it this way in order to get a high posterior to scientific theories. But again, he never thought you ought to be using this for any cases except when you had some kind of warranted strong prior for the null.
Well, I mean, I suppose there's not as... Jeffreys wrote about this more than once, so we might draw different conclusions from different things he wrote. But I was thinking about his probability book, and in his probability book, he kind of puts it in the context of what Fisher called multiple regression, or what we call multiple regression.
The parameter, the coefficient in a regression,
Yeah, so we're testing.
That's right.
We're testing whether a variable, something, is negligible. We're testing whether this variable is negligible.
Or not.
And substantively, it might often be the hypothesis we might be interested in testing is, does this variable matter? That's like, the variable does matter would be the hypothesis that the scientist would often be interested in.
They usually are, and they usually try to reject the null for that purpose. But these tests very clearly are making use of this point null, or if not exactly a point, some small range around it. This is how they're getting their result, which is creating the war. So,
Maybe
but
they're giving a-
yeah. So show me at some point, you know, what other kind of example. Yeah, but I know what you mean. Yeah.
Yeah, it seems to me, I think, a lot of these kind of debate between the frequent and the Bayesian, it's just, in fact, they're using different models, right? The prior is part of model assumption. If you have a strong prior, in which way, actually your assumption is already different. We expecting have different results. How could we expecting the same thing? Unless you use, as you mentioned, this like a diffuse prior, so there's not much information from prior getting into it. So all the information coming from your likelihood from data evidence. So then the agreement, you will see much more kind of p-value and posterior getting together. It seems to me, in that sense, actually, from confidence point of view, what we do in confidence distribution seems that really match.
That they do match, or they
would match if you
they
have
would
very
match
if you have very diffused priors.
That's right.
Yeah.
That's right.
If
and
you
that's
have
the
a
point.
strong prior, then it's just different model assumption. So if you do have strong evidence saying that, other evidence not from data saying that the prior is important, then that's fine with what you do. But a lot of times it's not the debating people are talking about, right?
But remember, you know, I'm specifically taking this up in terms of how this argument is used by the critic of significance test.
Right.
To say why they're exaggerating.
I don't agree with that.
And many of the people point out that they say scientists would not give this high prior, that when they talk about these coefficients like in a regression, they might mean it would be very interesting to know if it was 0 or if we can leave it out of our model or something like that. That doesn't mean that they think it's probable in some sense. I mean, Casella and Berg are trying to imagine what they would mean by the prior, and say they don't think that matches the way scientists use these. Yeah. But they're giving this criticism, and remember, I'm talking about how to understand the statistics war, the debates that are now taking place, and that's what I'm pointing out. This is how to understand them. But we do need to reformulate tests. For starters, p-values don't give us the effect size, and I propose to give this severity function, which is a function to test the data, and a certain claim of interest, and tests should be reformulated in terms of a discrepancy, gamma or something, from the test hypothesis. Instead of a binary cutoff, the particular outcome is used to infer discrepancies that are or are not warranted. And this is something I've developed for a long time. And I thought maybe a good example, because we talk about Jeffrey Lindley paradox, which really is a problem with large N, is to see what happens to avoid fallacies with the large N. It's true that if you keep your p-value fixed and increasing the sample size, the cutoff for reaching, whatever p-value you pick gets smaller and smaller, to the point that it was going to be closer and closer to the null than various alternatives. And many would recommend lowering the p-value requirement as n increases. And there's lots of discussions on this. And I.J. Good, who is my colleague for many years, had his way. Cox and Hinckley have their own, and there's some new ones. But I'm deliberately wanting to say, suppose we don't do that, we'll still be able to avoid inferring a discrepancy beyond what's warranted in terms of the severity. So very informally, severity tells us that an alpha significant difference indicates less of a discrepancy. I always use discrepancy for the parametric difference from the null if it results from a larger sample size rather than a smaller. An analogy: what's more indicative of a large effect? Maybe a fire alarm that goes off with burnt toast, or one that doesn't go off unless the house is fully ablaze. And that the larger sample size is like the one that goes off with burnt toast. It's the more sensitive one. But which one is actually more alarming? The insensitive one, right? At least if the assumptions are met. Because that might indicate to you the house is fully ablaze. And so that's what severity does by formal means. What about fallacies of non-significant results? It's true that failing to find a significant difference doesn't warrant zero discrepancy from the null. That's because there are discrepancies that the test had little probability of detecting even if they were there. But using severity reasoning, we can rule out discrepancies that probably would have resulted in a larger difference than observed, and thereby use the negative result to set an upper bound. Okay, so it's not just uninformative. That's loosely the idea of using the severity to reformulate tests. I have a numerical example, but let me just say that this is going to be somewhat similar to confidence intervals, but I think that, okay, you want to ask your question?
Is there any mathematical formula to define this severity in this specific example?
Yeah, I have it on the next.
Oh, okay, sure.
Okay, because I had sent it. I didn't know whether, you wanted me to get into it, but it's on the next. That I do think that that confidence intervals also get the associated reinterpretation. After all, confidence intervals have this duality with tests. Values within the 1 minus alpha confidence interval are the values that are non-rejectable at that alpha level. But the way these intervals are often used, not the way Minger uses them, are often too dichotomous, just like the kinds of dichotomous tests that they don't like. In or out, plausible, not plausible. Also, they get their justification in terms of this performance long run, whereas I give them an inferential interpretation. And I think that the idea of fixing the confidence level, which again is standardly done, is too rigid, that we should have many levels like Minger does, okay? Okay, so so here's a numerical example, okay? Well, it's one-sided normal testing. This was the water. We want to see if it's bigger than 150 degrees. And with this sigma 10, n is 100. So you would reject, let's say, whenever you get 152, I'm just going up to the 2 standard error, okay? And m being the sample mean, because the x bars are 2. And the 1 standard error is 1. So imagine we just reach the cutoff. And the reasoning I gave for significance test reasoning at the beginning, okay, that the usual test would say we have at least some evidence for the alternative, for mu being greater than 150. That's because the probability that you would have gotten a smaller sample mean than you did if the data came from a universe where H0 is true is pretty high. So that's okay, and that's where tests stop. That's where the Newman Pearson stops. Okay, but we would like to know, I say that it's not an effect size, and you would really like to have something more informative. So for example, would we be warranted in inferring mu is greater than 153 or something based on the observed mean of 152, okay? And so the severity says, so we're trying to evaluate the severity of this assertion, mu is greater than 153, okay? And what severity tells you to do is compute the probability of getting a worse fit with the claim if that claim were false. The probability of getting an m less than what you got, okay, if the claim was false, gives you this. But we can compute the severity at mu is equal to 153 because this probability would only be greater for values of mu strictly less than 153. So severity tells you to compute this. And in fact, we see we have terrible evidence because the probability of getting a smaller, sample mean under the assumption of 153 is 0.16. The other way to look at it is 84% of the time, if we were in a world where mu is 153, we would get a larger sample mean than we did. If we were in a world where mu was even just 153, never mind greater, then with high probability we would have gotten at least 84% of the time a higher sample mean than we did. So we block going, this is would be making mountains out of molehills if we went to 153. I'll give you the relationship with confidence intervals in a moment. Okay, I had that already, sorry. But to take just one more example, what about how warranted mu greater than 150.5? We're still talking about the observed mean of 152. It's just statistically significant. And again, we're asked to consider the probability of a worse fit with that claim, given that claim is false. And we work it down. And now it's pretty good indication, which is the word that I use, because we don't know about the assumptions holding yet. It's a fairly good indication that mu is greater than 150.5 because with fairly high probability, we would have gotten a smaller difference than we did if mu were only 150.5. So this suggests, with the usual testing reasoning, the exact same testing reasoning that we always use, that we have some evidence. And so you see it blends estimation with testing. Akin, I think, yeah, well, I don't know who's first, but okay.
I just have a clarification question, which is, are these three tests that you just ran supposed to be thought of as part of the same testing procedure, or is this an illustration of individual tests?
Well, it's a good question. What I'm trying to say is that in the midst of interpreting this one test in terms of the discrepancies indicated or not indicated, we are led to various questions of interest. Does this indicate this? Does this indicate that? I suggest that at least one bad inference be conveyed, that we would not have inference for evidence for such and such discrepancy, and at least one good one. But the exact status of these, a lot of people ask, I see them as, again, questions or claims that might be of interest in trying to interpret the rejection or the non-rejection. So far here, I'm just talking rejection. Yeah. Oh, I'm sorry.
It looks to me that what you're calculating as the SCB for this example is 1 minus the power function.
1 minus the power, did you say?
Yeah.
You're right, but that's only because I've decided to have the outcome be exactly at the cutoff. But I find that's much too coarse to always go back to the power. I want to go with the actual outcome. Because I made the actual outcome at a standard cutoff, it is the same in this case as the power. But I'm also going to want to consider the actual outcome I got, 153, 154, whatever, or the other way around, 151, 150, 149. But that's a very good point. But I find it's too coarse to just look at the power, which either gives you the worst case in a non-rejection, and see what I mean?
But I guess I'm wondering if, in general, if that's how SCB is defined, can we reconstruct this from functions of the power function?
You could, but not. The answer is no, because of the fact that I want it to be data dependent. So the best thing really would be for me to point that out to you, because this is exactly why I move away from the power. because especially with negative result, if you do power analysis, you might be forced to say, because it didn't have much power to reject, that this non-rejection isn't good evidence for some small discrepancy. But in fact, why look at the power if your actual outcome is even smaller? That's especially so in the case of negative result. Here we're talking positive result. But even with positive result, I had said that we had terrible evidence for 153, that mu is greater than 153. But what if your outcome was 156? I wouldn't want to just look at power at 152 in order to appraise mu is greater than 153 anymore, knowing that I got m 153. So the appraisal is going to depend on the outcome.
Please stay with this for a little longer. I'm really way behind because the term worst fit is not.
It is, and I would.
Well, no, I'm just not getting
Yeah.
it. M equals 152 is the observed value.
Yes.
Correct? And so what does worst fit mean?
Yes, that's right. First of all, I want to say that I almost never present an example like this when I'm giving a talk, but because this was this quantitative thing and I sent it in advance, I thought if they want me to give an example, I will. But I totally agree that it needs a little more attention, that the idea is to say that if you reject, we're saying that the observed mean is in accordance with the alternative. And then a worse fit is actually something that is, in this case, smaller. But again, I totally agree that it was something that
I'm not making an assertion.
either the whole talk has to be on, or, okay, but let me just say something about, let me just show you one thing about the sample size, because that was the point. Okay, so this is from the book, and the example I just gave is actually intermediate from the ones that I show in the book, showing you how to compute severity for the different claims. Is around page 140. With the sample size, quick example, because this is really where the Jeffrey Lindley thing comes in. It's with this large sample size. Comparing n is 100. This is the burnt toast, but now with numbers. Example. Comparing n is 100 with n is 10,000. And if we keep the standard deviation the same, but now we will reject with 150.2 because the standard error is 0.1. Okay, so let's imagine that, again, we just make it to the, it's not 5, we'll call it 5%, but it's more like really 3%. Okay, I'm using the 2 standard deviation cutoff. All right. But now n is 10,000. If you were to compute the severity, so here I'm indicating the sample size, for this one and the same claim, mu is greater than 150.5, okay, we had said it was pretty good with a sample size 100, but with sample size 10,000, if you do the computation, it's a terrible indication. Okay, and you can also see it with the confidence interval. Why would you want to say that, it's good evidence for this using your confidence interval? And so the severity is actually 0.001. Now, I've been doing just rejection because it's easier to have one in your mind than to have the other one, the non-rejection, also at the same time. But I agree, you really need to look at the paper. Yeah.
Yeah, this is very interesting. I think depends on which side test you're doing. So this is what your severity calculation is. If it's a one-sided test, then it's corresponding to the either p-value function or 1 minus p-value function. And in that case, exactly the confidence distribution kind of blended in.
It is.
Yeah. My question for you is how about two-sided test?
How much fun?
If it's two-sided test, what kind of severity function?
For the p-value?
Yeah. what you get from here? Is that
It's,
going to be,
it's the same. Did you say, you mean if you're using a p-value?
if you use p-value, but there's a two-sided p-value, right?
Oh, well,
In that
the
case-
two-sided p-values to me don't mean anything.
Okay, so you
Really?
still, if it's two-sided test, you still do this one-sided.
I like,
Interpret, okay.
yeah, exactly, yeah. But, you know, so as far as the connection to p-values, I think, as I say, how to do all that Neyman Pearson do and more using severity. And that reports on the work that I did with David Cox, starting from the p-value instead of starting from sort of Neyman Pearson. And it is exactly what you said. It's the p-value function. And the connection to the power you would also see if you look, if you write it down, yeah. So I call it something like the sensitivity function in order to make it data dependent. Yeah, sorry.
Oh, sorry, I was just trying to clarify on the vocabulary. Prior function means,
Yeah, it's related to p-value function. P-value function is more generally related, not kind of specifically highly to the one-sided test. Alternative or none.
are they, is one of them a function of the other? The p-value
Well,
function
yeah,
versus the
power
prior?
function is the right function.
Okay, I see, okay.
P-value
So
function is more general.
It's really just the probability that the p-value would be greater than it is under various different hypotheses. There's nothing to stop you from treating the p-value as a statistic and computing it over different alternatives. And the funny thing is how a Hsterian like David Cox is horrified at using power, but doesn't mind using these p-value, and it's really the same thing. Okay, so I just had a little sum up. Shall I look at it? That I say that to get beyond today's statistics wars, we need to understand this jumble of philosophical, statistical, historical, and other debates that are really largely hidden in today's debates, and also in the various reforms that we hear about that are supposed to restore integrity. There's the age-old significance test controversy, the Bayes frequentist battles, and then newer debates about the reconciliations, about default, subjective, and empirical Bayesians. And to evaluate the consequences of the reforms being put forward, I say we need to excavate this jumble and jungle as impossible as it seems. That's what I set out to do in this book. I begin with this simple tool that is actually underwritten by today's hand-wringing, namely what is too easy to find evidence for impressive-looking effects when it's spurious. The minimal requirement for evidence. A claim has to be subjected to and pass a test that it probably would have failed if false. Look at where probability is going. It's on the method. Biasing selection effects make it easy to find impressive-looking effects erroneously. They alter a method's error-probing capacities, I say. True, they may not alter evidence at all on certain accounts of evidence, such as traditional probabilisms, let's call them, following the likelihood principle. And so members of competing tribes talk past each other to the likelihood principle holder, worrying about what could have happened but didn't. The error probability is to consider, they say, imaginary data and intention. But to the severe tester, the probabilist is robbed from a main way to block spurious results. In fact, the replication crisis has had a constructive goal in showing this connection, that these come as a group. Biasing selection effects impinge on error probabilities, which impinge on well-testedness, not about long runs alone. This directs the reinterpretation of significance tests and other methods. Granted, probabilists may block inferences without appealing to error probabilities, like by giving a high prior probability to a null hypothesis and thereby getting a high posterior. But the severe tester sees that as giving a life raft to the p-hacker and seems to put the blame in the wrong place. Okay. severe probing, whether formal or informal, must really take place at every level. And I haven't talked about testing assumptions or specifics in moving from statistical to substantive, but really that's very important. When we hear non-replication, they often say, well, it's smaller effect, as if it's still evidence of a real effect, only smaller, but they really should be challenging whether it's evidence for a real effect at all. And I do agree, let me just jump to this, that many Bayesians are not probabilists anymore. In fact, Gelman sees himself as a falsificationist Bayesian, and here he is talking with Shalizi, who is an error statistician, and he says that at least parts of Bayesian analysis, like model checking, can be understood this way in terms of severe probing. So I'm not saying that everybody follows that, but this is what the wars have been about. And I'm prepared to say that a silver lining to distinguishing highly probable from highly probed is that different methods can be relevant for different contexts. I'm also prepared to say that some Bayesians may find their own foundations in error statistics, and the last excursion, I call it, in this book is probabilist foundations lost, at least the classic ones lost, probative foundations found. And that is the end. Okay. Questions?
So, very interesting. Really, I just always trying to figure out the like your severity function, how it's related to confidence distribution, that kind of uncertainty quantification. It seems there's a really very direct, very nice connection over there. It seems to me a lot of this debate is that why statisticians, to me, I just my limited understanding is the crossing each other. One is the model select, like model assumption different. That's the one thing. The other thing, like the cherry picking, p-hacking, this is actually you introducing who is doing this evidence is do the subsampling, and our actually when we do the p-value calculation is based on the whole sample, and when you do the evidence picking, cherry picking, is already select biased sample on some set. So if you take in those kind of bias sampling activities into the consideration, you will find out those p-value is wrong. You can be, if you the ideal word can correct them, then we could be coming back. But the problem is that people just subsampling and introducing that kind of additional randomness into the mechanism, and then that causes a problem.
So when you do the confidence distribution, you would adjust for these selection effects?
Yeah, we do have to consider.
You take,
yeah, the
okay.
model is right.
Okay, good. But now my question for you that I've been trying to ask you is whether you see this kind of construal fitting with your confidence distribution. Because I know that typically you give the performance-oriented justification, and I'm trying to say that you can say more. You can say something that's relevant to the particular inference. When we say, let's say that we have evidence that mu is greater than the lower bound of a confidence interval, let's say, we really want to say, here's why. Because if mu were less than that lower bound, with high probability, we would have gotten a smaller mean, or whatever it is, than we did. In other words, I actually want to say that we have evidence about the source of the data in the case at hand. And so that's what I've been trying to ask you, that whether you see that little bit of a leap, that's what the philosophy, the severity philosophy gives you, makes sense or is in sync with your...
I think it makes sense.
I'm putting you on the spot.
Yeah. Well, I think it makes sense what you just kind of talk about. To me, I'm always thinking from a little distribution kind of idea is randomness. Where the randomness coming from? When we do the inference, we try to mimic the randomness. Where it's coming from? Doesn't mean it's Bayesian or it's frequentist whoever, is the randomness where you coming from. And what you do with the severity calculation is kind of put it into this kind of randomness kind of.
Making it relevant to the case at hand.
Right.
Because what do we have in the literature?
Right.
You know, there's this website, Data Methods or something, trying to interpret results, and when they try to justify confidence intervals, you get this real rigmarole sort of thing that of course we can't say that 95% of the time this interval would contain the true mu, but we have to say something like, if this method were performed over and over again until you die and so on, that 95% of the time you would get it in there. And they say this is so unwieldy that clearly we need to use a Bayesian account. So I'm trying to say that it's very important to say what you can say about this inference, about the data generating mechanism in this case at hand. And that's what I'm trying to give.
Well, in that sense, it's conditional inference, right? Sometimes I would see my computer distribution is a sort of conditional inference too, because you're given the data on that.
Conditional?
In a sense, right? Bayesian is the claim is conditional.
Yes.
Right. Frequency is not conditional. You kind of look at the population. But then it's kind of everything seems to have two sides. Even, well, I don't know. It's a little bit more complicated.
You can be conditional physicist.
Right. It's more complicated, but I think probably don't get into it. But I do see.
Yeah. Yeah, and one of the things that's so interesting to me about your stuff is you've applied it into so many vast cases, and I say, well, that shows the mathematics is there.
Right.
That you could use this application.
That's
I can use his mathematics. And he does it for lots of fancy cases with, yeah. Okay, so we'll have to get together.
Right. Yeah, I think yeah. So I was also reading, trying to figure out what your severity the function, how do you define it mathematically? It looks like this example very clean. So it's it's pretty neat. Yeah. So in more complicated.
I know what.
So I
Well, here, see.
Two-sided, but you said you don't like two-sided. I think two-sided is much more complicated.
And just this really does show the connection with the confidence bounds.
Right.
Even more clearly, right? And where the M naught is the observed mean, the observed sample mean. I agree with Cox that you should see the two-sided as doing two tests, first one, then the other, and then adjusting. It really doesn't make sense. What do you infer? Only in the case where you truly didn't care about the direction would you ever infer there's some difference and I can't tell you what direction. And really, it's a very important, non-trivial point as to how some of these, the Bayesians, when they always use a two-sided, and yet they never report there's some difference, I can't tell you which direction. They always tell you the particular one, and it also matters because they would be using a different p-value if they looked at the one-sided. The whole analysis would be different.
It also Bayesian, I think I don't like when they do the testing that put the priors on H non or H effective, especially the space would be totally different, right? You look at the, like especially for two-sided tests, single point versus the whole thing, what are you talking about? Why you put the 50-50?
Well, that's what they do. It's supposed to be, it looks fair, but it's not. I mean, you have the point, you have 2 points, and they're not exhaustive.
Yeah.
And therefore, what happened to all the points in between?
Right.
And you're giving all your prior onto these two, and there's nothing left.
And the other thing is that when Bayesian doing the base factor and doing this, they also need to have a cut point, like threshold. Cutting is similar to the significant test. To me, it seems to be corresponding significant test, like 5% or 10%, things like that. It's very
That they also have cutoff,
similar,
right?
Yeah. So it's not like they're avoiding this like 95% or 5% issues. They're not. But
Yeah.
yeah, but it's
Other questions?
You mentioned this guy Goodman, I think, Stephen. I've never met. Have you met him, Stephen Goodman?
Who?
The guy at Stanford, you said, Stephen Goodman, who...
Ephron? No.
Goodman.
Oh, did I meet him? Yes. Yes.
I only know him through his... he writes... I'm very interested in history.
Yeah.
He has written some terrible history. And so...
he's not...
very influential. Wikipedia repeats his bad history about p-values.
Which bad history?
Fisher invented it. Fisher invented significance testing. For example, that's the most irritating.
So you think it's written from his kind of perspective? Is that what you mean?
Well, I've read what Goodman has written,
Okay.
and then I find the same thing. And
Okay, because he gets around. He gets around. But it's not just him. He's really a disciple of Richard Royal, who I mentioned, and he's in my first chapter too, because he's a likelihoodist, but he was very influential, and he's really pushing the likelihood principle to the death, saying that there's no more evidence except what's in the likelihoods, and it's the standard.
My question is, how do we get Goodman to know that his history is very bad?
That's Jim said. How did we get such a messed up history about?
How do we let Goodman know about this? Do you know him?
Well, you know what? I have actually, I have sent him, first I sent him my book, but I sent him my criticism of him over the years. I was at this conference for A World Beyond P-Values and all that, and he was there, and I always tell him, I always show him, and I was at the powwow, I call it the P-value powwow, where it was the American Statistical Association trying to put together those 6 principles. Yeah. I was the philosophical observer, and of course Steve Goodman, was there, and I showed it to him. I never absolutely, I'm sorry I didn't absolutely say, well, answer, so what do you say? But I didn't exactly, but I've shown it to him. And there's a lot in this book, but it isn't so much that he invented it. It's a very classic line about the import of the evidence that we see in any classic Bayesian or likelihoodist. And when we were developing logics of induction, when that still seemed like a viable project, as with hacking, you could see why I think philosophers would gravitate toward that kind of thing. Because they were looking for relationships, confirmation relations, that held between hypothesis and evidence. And you shouldn't really have to know how you got the hypothesis, how you got the data. This was the classic idea, the discovery justification distinction, and all of that. And it kind of made sense. I don't need to know how you got it. And when people...
Was Goodman trained as a philosopher?
No, he's not. I'm just saying that there is a history on the philosophy side. And when this was questioned then by people like Popper and the Popperians, who said, everything we worry about with respect to ad hoc hypothesis, where you saw the anomaly and you deliberately fixed it, is relevant. In other words, they started to say the history of the hypothesis is relevant. And they called themselves, the historical confirmation account. And they didn't really have other words to use to say we should care about how it got there. So there is this parallel in the philosophy that I try to trace out as to why that made sense, or at some point in that project of induction.
Yeah, I don't know, maybe everyone might be interested to talk about history. Glenn is here, you're here. So who first started with p-value? Is probably not Fisher, right? Pearson had publications earlier than that.
They did use it before that.
Right, so
but
he's not the first one.
Yeah, well, I'm not going to be able to then give you the exact on that, but maybe somebody else can. Yeah.
Or especially two-sided p-values.
The term p-value comes from the 1970s.
It's actually, I was going to say it's later, but I don't think it can't quite be that late, I don't think.
So.
There was an article that, where Eric Lehman is talking about it, and I think it's the 60s, but whatever.
Well, okay.
Everything happened in the 60s.
The value, here's a formula. P equals. What is the value of P? So Fisher talked about the value of P. Is the value of p the same thing as a p-value?
I see, and they did have different notions.
But
There's a place where I saw
But
layman
the term significance testing,
calling it, yeah.
the term significance testing was in textbooks by 1900. Before, when Fisher was 10 years old.
That's interesting,
So
yeah.
Fisher did not invent
Right.
the term significance testing. It actually originates with Edgeworth. Significance.
They should blame these other people. But, you know, there's a lot of people now who are very touchy about words, and they're writing petitions that we should all sign, that we should never use the word significant and never use the word confident. And I've been asked to sign a bunch of these, and I say, I don't like signing against using words. And they're quite mad that I won't sign.
Okay, I have a word issue.
Good?
I have an issue about words.
Okay,
It's really a proposal.
yeah.
And the proposal is that we stop using frequentism as the opposite of Bayesianism.
Yeah,
And
yeah.
and I cite as a point in favor of my proposal that von Mises, Richard von Mises, was a Bayesian. And if there's anybody who believed in the frequency theory of probability, it was Richard von Mises.
Yes.
So there's a serious confusion. I mean, everybody, we all talk about frequency.
Well, that's why I called it the error statistician, because I'm trying to be very clear that it is not merely a hodgepodge of frequentists. Because what you see now are exactly what you say. The Bayesians who say we're frequentists too, and their priors come from things like selecting a hypothesis from an urn of null hypothesis, which is really a completely different meaning, even though it has frequency.
I didn't realize I had a proposal. I didn't realize.
I agree.
I did not realize that my proposal was a rival to yours.
No,
But no.
I hope not.
I have a different replacement.
Okay.
So what's the word?
And my replacement was was used by von Mises. He called it Bernoullian, which matches Bayesian. So it would be much more historically convincing, Bernoullian versus Bayesian. So Bernoullian doesn't talk about it's not whether it's a frequency or subjective, it's what the method of inference is. And Bernoulli had a method of inference, which is Bernoullian, which is not Bayesian. So that's my.
But I'm not sure what it is.
What is what it is?
No, Bernoulli-ism inference.
Yeah, so Jacob Bernoulli had a way of inferring how many black balls there were in the urn.
And it's similar to a Carnapian, or
Law of large numbers.
okay.
That was the first non-Bayesian, and before Bayes, the first non-Bayesian inference about how much, 80 years before Bayes is Bernoullian. Anyway, that's fine.
But what do you think about this this error statistician notion?
Well, it's a name, as I say, I didn't realize when I started talking about this that Bernoullian would be a competitor to your term, error statistician.
No, it might not be. It might not be different, but I do think that.
No, I think it sounds like the same thing, but it's.
But there's a very different goal, because I want to be able to say, this hypothesis is very believable, and maybe I even know it's true, but it's been poorly tested. A little bit like what we say in courts of law, where somebody just didn't make the case. They did not show that they took seriously plausible threats of error. If you follow that line all the way through, I do think it's significantly different.
So Bernoulli was doing more of a confidence interval, you could say.
So it is, yeah, it's here where I said that, yeah, okay, here. That these error probabilities, I call them I call it error statistics because it's reaching inferences based on something about the error properties of the method. It's a methodological probability, which
That was Bernoulli's idea. I mean, he was saying, I can sample from this urn enough times that I won't err, that I can be, he may have even used that term, I don't know. It's, I can be as sure as I want to be that you know, there are this many red balls, there's this many white balls in the urn.
There's always been this issue, though, about the move from, if I keep doing it, I'll be right with high probability, and what I can say about the case at hand. That is one of the central things that I've tried to address.
It wouldn't be fair to say, I mean, he was very interested in the case
Huh?
of Andy. It's this urn.
It's this urn, and I say that if I kept going, I would get it, and so I've stopped.
I'm going to keep going. Tell me how far I have to
Oh, I'm going to keep going.
I'm going to keep going. Tell me how far I have to go. Here's how many I have to go.
And I make an inference.
And I will do that.
And I'll make the confidence interval, but so what do I say about that interval?
Well, it wasn't a confidence interval, actually. It was 200. It was how he wanted to
Yeah.
do it. He knew, I mean,
I know.
in his example, he knew there were 100, he knew there were 50 balls in the urn. And he wasn't looking for a confidence interval. He wanted to know how many of the 50 balls are white.
How many of the 50
Are white.
are white? Yeah. And so you make this, it's an estimate, you make this inference to the estimate, and you qualify it in terms of.
No, he said, tell me how sure you want to be. Okay, you
Yeah.
only want to have a 1 in 1,000 error, chance of error. Tell me that. Okay, I'll tell you. You need 20,000 draws. Make 20,000 draws. I am absolutely sure, I'm absolutely that sure that there's, the number of white balls is 30. That was his problem.
Yeah, but if you think about it, so what you say that here's a method that is right 99% of the
I'm trying
time.
to get James Jacob Bernoulli to be your ally.
No, I think he is, but there's this little move, there's this little gap that I've wrestled with for 5 years. I mean, sitting there thinking about it, there's still a little bit of a gap between what you say, I'm so sure because 99%, I would not have gotten this. It was something like that. So I'm trying to just fill the gap. I agree with the spirit of that. I don't know. How else?
We need to introduce the concept to statistics because the errors of statistics is in this community, not like really people have been using that word today. So, I mean, in statistics community, probably you should give more talks in statistics conferences.
I should give more talks about.
In statistics conferences about introducing this error probability, error statistics kind of concept. Yeah, and the other thing I was thinking is that probably if you can show exactly formulas, some sort of formulas more, like the example what you showed, it would be really good to get
but
the,
I mean, please do look at the book, but I don't think that most of the time talks want to look at formulas. I mean, I sent them in advance, but I think that I always feel I'm boring everyone if I start, unless they've really looked at it and they're familiar with it and they want to see how I would do it. I don't know.
well, yeah, I don't know. It's sometimes,
But I did a little,
yeah, like the
I'm happy
example
to.
is much more clear. Yeah, well, I was always reading it. Sometimes there's so many things you went through, so it's kind of you don't know which.
So is this, how about this example? Is that
This
pretty,
is very
is that
good,
okay?
it's very good.
Yeah. And I was going to do the negative result, but I think when you try to do both, unless you're familiar with it, it's a little bit dizzying. I mean, I don't want people to walk away and think this looks very hard. It's actually what's already there. As I say in the book, you might say that this is just what a judicious use of error probabilities would be like. And I say that's what the error statistician said. To me, it was a rule of thumb kind of a thing that I developed as a graduate student learning statistics. I was in philosophy. I wasn't planning to do any statistics, but I was a math major, and I'm sort of taking it to deepen my understanding of some of the classes I was taking on confirmation theory, take something in probability. I wasn't planning to go whole hog in statistics. So this was kind of developed as a rule of thumb for me to understand results. And I assumed everybody does it anybody would do it this way. So it really isn't different in some sense, but it does go hand in hand with a philosophy of science that is different from any kind of probabilism or assigning probability or saying that inference is a confirmation boost. It's much more in a falsification spirit, although we do have corroboration, and although Papa was right to say that we have evidence for a claim if it's corroborated, meaning it probably would have been falsified if false. He actually never had an account that could make sense of that at all. He was such an anti-inductivist, he thought you could never say a method was reliable. So he had this idea about corroboration and falsification that he could never cash out. So you could see this as trying to cash out this Popperian idea of corroboration.
So who are the other philosophers who are interested in statistical inference today?
That's a very good question. You probably know more than I. You know, our field is an odd one because when I started out, really, philosophy of statistics was ahead of its time in the sense that practitioners in statistics were working hand in hand with philosophers of science. Isaac Levy, Teddy Seidenfeld, I mentioned Ian Hacking, Fetzer, Geary, lots of people. And it was also intimately involved in building our philosophies of science. And now, I don't know, formal epistemology, I think, has moved away from the practical, from the practice, and from these wonderful debates that are going on in statistics. And, you know, I want to try to remedy that. My colleague and I are doing this this 2-week intensive workshop in the summer that are intended mostly for philosophers or social scientists. In fact, if you don't mind, I'll pass this around since you brought it up at just the right moment. And because I think that they're blocked from having a say. I was the only philosopher they could find for that powwow. And when I was at the Philosophy Science Association meeting just a few weeks ago, I had a special lunch on this topic, and I got lots and lots of people. Of course, they're interested in different aspects of formalism, and we've always been interested in formal stuff in philosophy, but I do think that there should be a return more to some of these issues, especially with things like experimental philosophy being popular and using these statistical tests to appraise philosophical theses. Okay, so I don't know. So who would you say now?
Well,
it's tough.
It was a real question.
Yeah.
I have, I had more contact with philosophers in the period you're talking about when we both started, and I'm just now coming back to talk to philosophers, and I can't find anybody. It's true.
Well, that's why we have to cultivate them. I'm serious. But I also think there's, at bottom, an obstacle because as technical as they are, they won't be, they're not all technical, they're mostly not technical in this, in statistics, and that's why we want to, that's why I want to provide this opportunity, and we'll see what happens. Yeah, they do all this physics. But again, the weird thing is, I mean, philosophers of science have said that our job is to deal with conceptual confusions of scientists, especially as we swore in post-positivist days that we were really going to be relevant. We're going to be relevant to science. And here we have cases every day where they're debating the deepest methodologies to be used in science, and the philosophers are pretty much nowhere to be found. So smart philosophers would say this is a good thing to pursue. But you know how it is with fields. They go along with whatever the problem is today, and if somebody's not doing it. So, okay. That's for the future, yeah.
Can you start with a follow-up question? How do you develop philosophy doing?
How do I do?
How do you view formal learning theory and statistical learning theory? Those people who are dealing with machine learning.
Yeah. You know, I'm not sure. There's some of the debates, like in data science, we were talking about is that a new paradigm or not? Some things that I really want to look at more. And the whole issue about when data dependence is okay, because that's what they do, and it's not always pejorative. It's something that I need to look at. So I'm not totally sure. I do think, though, that much more attention has to be paid to the assumptions of those models, right? What do you think of the formal learning?
I feel like there's much commonality, common ground between the two that is often recognized.
Which two?
The formal learning
Yeah.
theory, they sometimes pitch themselves against a sort of statistics.
So formal learning means, you're not
Is
talking
that
about
machine learning or?
are you talking about a philosophical subfield or a computer science subfield?
Both, I was thinking.
Oh.
Formal learning meaning the thing that Kevin Kelly in particular was doing, where you sort of get everything in terms of simplicity.
Did you say the Kevin Kelly stuff? Because I think that's yet another kind, isn't it, from what the AI people, although...
Yes.
Yeah.
Yeah.
I have trouble linking it up with practice or with statistical inferences.
Apparently that's what they're trying to do. So they're trying to...
That's what they're trying to link it up.
They're trying to link it up.
Yeah.
Yeah.
I hope that, I mean, I've talked to him many times over the years, Kevin and the people there, Carnegie Mellon. But I'm not sure. I need to pay more attention to what they're doing in AI, but as far as whether they're going to connect to what he's doing, I'm not sure. I think that, I don't know.
My impression is that the cycles in philosophy of science that corresponds to statistics and other things, they kind of correlate with the cycles in science themselves. Like,
Really?
I think maybe scientists were talking about falsification, induction, early half last century, I think, even later. And they moved on to other debates, say in biology, in physics, in chemistry. There are new philosophical issues that come up that draw people's attention. And I guess maybe the recent debate about p-values and psychological experiments not being replicable could be the source of attraction to some people to go into this again. But I would think that it needs something big to draw people into this again.
So you think this is big enough?
I think so, yeah. Every time you see nature and stuff.
Yeah, I hope so. I hope they're not too late, though. I mean,
But I
yeah.
see my peers in philosophy of science, they're all engaging the cutting edge hot topic issues in conceptual foundations of, say, physics or biology. And it's very rare to find people who are interested in just learning theory or the old problems of information. And there's still some, but they're the minority now.
It's hard to give a whole analysis, but I mean, I think that we did start to focus more and more on particular philosophy of biology, on particular, applications, and now ethics stuff, climate change, and so on. But I think the generality is importantly missing in philosophy of science, and has for a long time. I mean, back to the big questions and the problem of induction and how we learn from theories and models and statistical inference and so on. I think it's been somewhat of a cop-out myself.
So Eddie thinks that philosophy is accurately gauging what's important in the world of science.
I don't think it's always that accurate, but it's always some fashion, it's always some crisis.
The funny thing is some of these outfits, like take with the with Diederik Stapel controversy, the guy who the social psychologist who didn't even collect data, and they had this whole report on him, and they said, really, we have to insist that researchers take philosophy of science in order to understand what verification biases are and what pseudoscience is and demarcation and all these things that philosophers have pretty much given up on. So so I say in my book somewhere, let's not tell them that we've given up on these, because they're saying we really need to associate, we need to assign them philosophy of science, and they probably assume it's there somewhere. It ought to be. I mean,
Difficult issues.
Yeah. Let's not tell them. Thank you very much for giving me so much time and attention.